Hello dear students, I welcome you back for lecture number 2 on the topic electric charges and field. So earlier in this topic we had discussed what is a charge and what is the property of the charges. In that we had discussed one important property, that like charges are always going to repel and unlike charges are always going to attract. But do we have any idea by how much force are they going to attract and by how much force they are going to repel? So in order to know this, today we are going to study a very important topic, that is Coulomb's law, or it is in common language it is called as electrostatic force. Coulomb's law. Now consider 2-point charges. Imagine this is charge Q1 and another charge Q2. They are separated by a certain distance r. Now both are like charges, so it is quite clear that both will undergo repulsion. So what will happen? This charge Q1 will exert force on charge Q2, and as a result this Q2 will experience a force in this direction. Let me give that force a name, F21. F21 indicates force on second charge particle due to first charge particle. Similarly, so if action is done on this charge particle, whether this charge particle will keep quiet? No, he has to give back the reaction. From Newton's third law of motion, for every action there is always equal and opposite reaction. As a result, this charge will experience a repulsive force. Let me give a name, F12. F12 indicates force on first particle due to second. Now this force will be always equal but opposite in direction, from Newton's second law of motion. So Coulomb's law, before going to the Coulomb's law, let me give the statement. So what does it states? That the electrostatic force of attraction or repulsion between any two charges is directly proportional to the product of the magnitude of the two charges and inversely proportional to the square of the distance between them. So let us study this in detail. Now this is the overview of the Coulomb's law. Okay, let me do a little bit of mathematics here. Now you know that the force of repulsion, here I am talking the word repulsion because I am considering two like charges, will be directly proportional to the product of the magnitude of the two charges. So this repulsive force depends upon the product of the magnitude of two charges. Now you can compare this law with the Newton's law of gravitation, because earlier in the first lecture we had seen that we had compared a charge with the mass. So what Newton's law of gravitation tells you, that every body is going to attract every another body by the product of their masses and inversely proportional to the square of the distance between them. So here this Coulomb's law and Newton's law of gravitation are quite similar. There we are considering mass, here we are considering charge. So this force will be directly proportional to the product of the two charges. So if the magnitude, so the force depends upon the magnitude of the charges. So out of Q1 and Q2, if Q2 has more charge, so definitely this charge will experience more repulsive force as compared to Q2. So this electrostatic force of attraction or repulsion depends upon the product of the magnitude of the two charges. It also depends on, or it varies inversely to the square of the distance between them. So if the distance between two charged particles is very big, then the electrostatic force of attraction will be very weak. And if the two charges are very close to each other, then the electrostatic force of attraction will be very strong. So F is proportional to Q1, Q2 divided by R square. Yes or no? Is it clear? So this is very easy to understand. So if two charges, if the distance is huge, if I keep one charge here and one more charge some 1 meter apart, then the force will be definitely weak. The same charge if I bring very close to me, maybe 0.1 meter, very close to me, then the force will be stronger compared to that 1 meter. Okay, so here we are not talking in meters. Okay, this force will be valid in case of only in the order of 10 to the power minus 15 meter. Please take care of this, because earlier I had told you this is a part of quantum mechanics in which we are dealing with micro objects. Okay, so when I say micro object, the distance also should be considered in micro terms only. Anyways, the electrostatic force of repulsion or attraction is directly proportional to the product of the magnitude of the two charges and varies inversely proportional to the square of the distance. This Coulomb's law is also known as inverse square law because of this reason, because F varies inversely proportional to the square of the distance. Now, students, see here, if I remove this proportionality, I am going to get one constant K. Let me give the name K. Q1, Q2 divided by R square. Where K is known as electrostatic force constant. Where K is known as electrostatic force constant. And experimentally, K, value of K is found to be 1 upon 4 pi epsilon naught Q1, Q2 divided by R square. So throughout the topic or throughout the syllabus, you have to always remember the value of K is 1 upon 4 pi epsilon naught Q1, Q2 divided by R square. I'll come back to what is this epsilon naught. Epsilon naught is permittivity of free space. We'll discuss later on what is permittivity and these all things. Now, this value of K is found to be 9 into 10 to the power 9. 9 into 10 to the power 9. Put the SI unit for this. Force will be Newton meter square per Coulomb square. So value of K is found to be 9 into 10 to the power 9 meter square per Coulomb square. Okay. Now this value of K depends upon the medium. So this value is not a constant. It varies from medium to medium. Depends upon where you are placing the charge. If you place the charges in a air or in a vacuum, then the value of K is found to be 9 into 10 to the power 9 Newton meter square per Coulomb square. If the same charges you are placing in a glass is directly proportional to the product of the magnitude of two charges and inversely proportional to the square of the distance between them. We expect you to write the statement as it is, because since it is a law, we expect you not to modify in the statement. Remember, the electrostatic force of attraction or repulsion between two charges is directly proportional to the product of the magnitude of two charges and inversely proportional to the square of the distance between them. So remove this proportionality, you are going to get a constant K, which is known as electrostatic force constant, where F is equal to K, Q1, Q2 divided by R square. So value of K is 1 upon 4 pi epsilon naught, where epsilon naught is permittivity of free space. I'll come back to permittivity concept, don't worry. Right now you have to by this value 8.854. Sorry, I forget to write one thing. It is not 8.854, it is 8.854 into 10 to the power minus 12 Coulomb square per Newton per meter square. Sorry for this. And value of K is 9 into 10 to the power 9 Newton meter square per Coulomb square. Remember, this value is only valid in terms of when the charge is placed in air or in a vacuum. Okay. Now students, looking at this, can you define what is 1 Coulomb? Then can you define what will be 1 Coulomb? Can you define 1 Coulomb? So, see here, if Q1 is equal to Q2 is equal to 1 Coulomb, when the distance is 1 meter apart, then the force experienced by the charged particle will be 9 into 10 to the power 9 newtons. This is the definition of 1 Coulomb. So 1 Coulomb is that charge which, when placed at a distance 1 meter apart from similar charge, experiences a force of 9 into 10 to the power 9 Newton. So that is the definition of 1 Coulomb. So 1 Coulomb is that charge. 1 Coulomb is that charge which, when placed at a distance 1 meter apart from similar kind of charge, so that charge will experience a repulsive force of how much? 9 into 10 to the power 9 Newton. So from this equation you can define 1 Coulomb also. So is it clear? Have you understood what is Coulomb's law? Remember, the electrostatic force of attraction or repulsion is directly proportional to the product of the magnitude of two charges and inversely proportional to the square of the distance between them. So students, before studying Coulomb's law in vector form, let us understand what is point charge first. Because if you see the statement, I had used the word the electrostatic force of attraction between any two point charges. So what is this point charge? So when the size of the charged particle is very small, or I would say negligible compared to the distance between them, then the charge appears to be like one small point. Okay, that is called as point charge. Okay, So you can imagine this, or take an example. If somebody on the sun looking at our earth, okay, though our earth is very huge object, but somebody from the sun looking at our earth will also look like one small dot or like small point. Somebody from the galaxy looking at our sun, again sun though being a huge object but still appears to be very, very small because the distance is huge. Similarly, point charge is also same concept. The size of the charge particle is very small compared to the distance. Here I am comparing with the distance. Then that charge appears to be like a small dot, so I give the name as a point charge. So is it clear what is a point charge? Okay. So before wasting, let us not waste the time. We'll study Coulomb's law. Coulomb's law in vector form. Coulomb's law in vector form. Because this is a very famous question asked in the board exams. Usually in board exams they will definitely ask this question. Okay. So again consider two charges plus Q1, one more charge plus Q2 separated by a distance r. Again, as a result, this charge particle will experience a force F12. What F12 indicates? Force on charge particle 1 due to 2. This will experience a force F21. Yes or no? So this R, I'll put a mod here. Mod indicates it has magnitude, it has scalar, it is a scalar quantity. So let R1 be the position vector of this charge particle Q1 and R2 be the position vector of this charge particle Q2. Okay. Now consider two charges Q1, Q2, same thing. Okay. Then shall I erase this so that we can utilize spacing? Okay. So let F12 be the force on charge Q1 due to Q2. Yes or no? And let F21 be the force on charged particle Q2 due to Q1. Is it not? Yes. Let R12 be the unit vector pointing from Q1 to Q2. If you remember the diagram, charge Q1 is placed here, Q2 is placed here, RB is the distance, R1 is a position vector of Q1 and R2 is a position vector of Q2. So let R12 be the unit vector pointing from Q1 to Q2. Let what will be R21? R21 be the unit vector pointing from Q2 to Q1. So apply Coulomb's law here. Coulomb's law, what it states? What will be F12 will be equals to 1 upon 4 pi epsilon naught Q1 Q2 divided by R square 1 2. So this will be what? R21. See, force on charge particle 1 due to 2. So its unit vector will be 2 1 because R21 is a unit vector pointing from Q2 to Q1. Q2 to Q1 will give rise to force of F12. Similarly, what will be F21? I'll show a vector here. This will be 1 upon 4 pi epsilon naught Q1 Q2 divided by R square. Here I should write R12. So just put this in box. And this is one more. So I'll give this equation 1 and 2. So here equation 1 and 2 shows Coulomb's law in vector form. Okay, so it is quite easy. Here you have to just consider two charges. Again same thing. Charge 1 will exert force on charge 2. So that will be 1, 2, and this will be experiencing force 2, 1. So F12 be the force acting on a charge Q1 due to Q2. Let F21 be the force on the charge Q2 due to Q1. Let R12 be the unit vector pointing from Q1 to Q2, and R21 be the unit vector pointing from Q2 to Q1. This is very important, from where it is pointing and towards where it is pointing. So F12 is what? Force on charge particle 1 due to 2. Force on the charge particle 1. So 1 is experiencing the force. So from 2 to 1. And similarly F21 R12. Okay, will you remember this? Okay, so this is Coulomb's law in vector form. So equation 1 and 2 gives me Coulomb's law in vector form. Let me erase this. So students, while studying Coulomb's law, I told you that we will be discussing a concept of permittivity, which was denoted by a letter epsilon naught, which is a Greek letter. Now, you know the Coulomb's electrostatic force equation. What is F is equal to 1 upon 4 pi epsilon naught Q1 Q2 divided by R square. Now, if you look closely to this equation, you see that F is inversely proportional to epsilon naught, where epsilon naught is permittivity of free space. Okay, so if F is more, epsilon naught will be less. This epsilon naught depends upon the medium. Okay, so consider two charges placed in a vacuum, and same two charges placed in some another medium, maybe glass or water. You tell me where the interaction of the charge will be difficult. So in glass, since it is a denser medium, the interacting force will be weak because it's a denser medium. So this permittivity depends upon the medium. More the permittivity, less will be the force, or lesser the permittivity, more will be the force. So while studying Coulomb's law, we consider two charged particles placed in a air or a vacuum, where there is less opposition. So permittivity means what? Permitting the interacting medium to resist the electrostatic force of attraction. Understand? Permittivity means what? Not allowing the charge to interact, but permitting its own field to resist the electrostatic force. Have you understood what is this permittivity? So this value changes from medium to medium. Okay, permittivity means what? Allowing its own field to resist the interacting force. Okay, so if I place the charge particle Q1 plus Q2 in an air, and same charge particle plus Q1 separated by same distance plus Q2 in a water, you tell me in which case the force will be stronger. In which case? Obviously in this case force will be stronger because permittivity is lesser. In this case force will be weaker because water is denser medium compared to air. So the force within the charged particle will be less. Have you understood what is permittivity? So considering this, so we'll study dielectric constant. Okay. Now, dielectric constant is the ratio of the force between two charged particles separated by some distance in air or a vacuum to the force between two same charged particles placed in a medium but at the same distance. So what is dielectric constant? Here we are placing two charges with certain distance initially in the air, and again taking the same two charges separated by same distance but in some different medium. So dielectric constant is nothing but it is denoted by many letters like K, epsilon naught, epsilon R, or maybe epsilon naught also. Okay, in different textbook you will find different denotation. Let me give name as epsilon naught R. So dielectric constant is nothing but ratio. Ratio means division. ratio of force between the charged particles when it is placed in a air to the ratio of same two charges placed in a medium. Are you understanding? So dielectric constant is nothing but ratio of the force between two charged particles placed at certain distance in air to the ratio of force between same two charged particles placed in a medium but at same distance. Okay, so we'll do little bit of mathematics here. Okay, now force between two charged particles in air. So let me give a name of FA. FA will be what? 1 upon 4 pi epsilon naught R, epsilon naught Q1 Q2 divided by R square. Similarly, force between same two charged particles in medium and in same distance. What will be this? Fm will be what? 1 upon 4 pi epsilon naught. Epsilon naught is permittivity of free space. But here I will use one more term, epsilon naught R, which indicates it is the permittivity of the medium. This will be equals to Q1 by Q2 divided by R square. I'll give this equation 1 and this as equation 2. Look at both the equation. Are both similar? Yes. Only extra thing is epsilon naught R. What this epsilon naught R indicates that same two charges are placed in the medium. Initially I am keeping the charges in a air. I get 1 upon 4 pi epsilon naught Q1 Q2 divided by R square. Again I am placing the same two charges at same distance but in different medium. So you change the medium, air will be there. Obviously air should be there everywhere unless you are in the vacuum. So what will I get? 1 upon 4 pi epsilon naught into epsilon naught R, which indicates it is permittivity of the medium. So I get Q1 Q2 divided by R square. So look at equation 1 and equation 2. Are both same? Yes. Almost I would write FA is equal to epsilon naught R Fm. Correct? So epsilon naught R will be what? FA divided by Fm. So this ratio of force, it's a ratio of force. Which ratio? Charge particle placed in the air. A indicates air. Force ratio of the force of a charge particle in the medium. This ratio gives me epsilon naught R, which is known as dielectric constant. Okay. Now last concept that we are going to study is relation between absolute permittivity and relative permittivity. Now students, whenever I say the word relative, means it is quite understood that to have a relation, two things should be there, two or more than two. Okay, so relative permittivity and what is absolute permittivity. See here students, till now at the beginning we were studying Coulomb's law and we consider only air or a vacuum as a medium. But you know that when I placed a charge in another medium, the force weakens due to permittivity of the medium. That's what we are studying in a dielectric constant. So the permittivity of the air and the permittivity of the medium, they are forming one relation, and both relation is of permittivity. I together call them as what? Relative permittivity. And relative permittivity together will comprise one whole permittivity, which is known as absolute permittivity. Absolute wholesome permittivity. Let me write this in terms. What will be the relation? E epsilon is equal to epsilon R. Okay. So this is the relation between absolute permittivity with relative permittivity. Let me write the terms here. This is just epsilon. Epsilon is absolute permittivity. Absolute permittivity. What is epsilon naught? It is permittivity of free space. Permittivity of free space. Permittivity of free space. What was the value supposed to be? 8.854 into 10 to the power minus 12 Coulomb per Newton per meter square. Yes or no? What is epsilon naught R? It is permittivity of the medium. Okay, now it is clear, right? So this is the relation between absolute permittivity and relative permittivity. So we'll stop it. Okay, next class we'll study electric field and the significance of the electric field. So is it clear whatever we have studied today? We started with Coulomb's law. What does it state? The electrostatic force of attraction or repulsion between 2 point charges is directly proportional to the product of the magnitude of two charges and inversely proportional to the square of the distance between them. So I got F is equal to 1 upon 4 pi epsilon naught Q1 Q2 divided by R square. Also we have deduced the Coulomb's law in vector form. Okay, you have to remember the equation. Then we have studied the concept of permittivity. Permittivity means what? Allowing the medium to resist the force. That's it. That's what you have to remember. Then we have studied the dielectric constant. What is dielectric constant? We are just taking the ratio of the force when the charged particle is placed in a air to the force when a charged particle is placed in the medium. So when I get Fa by Fm, I'll get one constant value. That constant value is called as dielectric constant. Then we have studied the relation between absolute permittivity and relative permittivity. At the end I got epsilon is equal to epsilon naught into epsilon r, where epsilon is absolute permittivity, epsilon naught is permittivity of free space, and epsilon r is permittivity of the medium. Okay, we'll stop it here. Thank you.